Hello, so this is quiz 8, the last one, mostly about matrix games in game theory. So the first problem says solve this matrix game, and by solving we'll find the optimal strategy for the row player, the column player, and the value of the game. Here's the matrix. And you'll notice that this matrix is not strictly determined game because it doesn't have a saddle point. If you do the circling, the minimum in each row and the maximum in each column, you'll find out that there's no saddle point, which makes this problem kind of difficult. So we have to solve this the long way. And I've done the setup here. I personally think this problem is a bit too hard for this, because the level of this problem is not really presented in any of the course. I don't get to choose the problems in the quizzes. So it's kind of long, so we set up the solution set like here, minimizing y equals x1 plus x2 plus x3, and maximizing y equals z1 plus z2 plus z3, subject to these constraints. And the constraints are set up here. You notice this is the matrix. The minimizing the x, you set up the coefficients of x1, x2, x3 according to the columns. See, that's why there's -2, 1, -3, which is the first column. And then the second inequality will have these coefficients in the second column, 3, -1, -3, and likewise. And then maximizing the z, y equals z1 plus z2 plus z3, we do pretty much the same, but this time the coefficients are the rows. So -2, +3, +1, and then 1, -1, -2. See, they correspond to the rows of this matrix. So I'm not going to get into how we solve these. You can actually solve these by putting these in an augmented matrix, each one of these subject to inequalities as if they were equations, and then reduce those matrices to an identity matrix, and the right hand side will then give you the solution, which is here. So I didn't want to spend too much time doing those, but here x1, x2, x3 would be this is a matrix, by the way. We're not adding, subtracting these. This is a matrix. So x1 would be -25 over 22, x2 would be -5 over 11, and x3 would be -9 over 22 when we solve this inequality. And when we solve this system, we get z1 equals -1, z2 equals 0, and z3 equals -1. And then in order to figure out P star, the optimum strategy, and Q star, all we need to do is figure out V and multiply each entry of X with V, as you see here, and same thing here, multiply each entry of Q with the V. And V can be calculated in two ways. You either make it 1 over Z1 plus Z2 plus Z3, or 1 over X1 plus X2 plus X3. Seeing that the X values are, kind of complicated, they're fractions, it would be really hard to add those. I mean, not too hard, but adding Z's is relatively a lot easier because you get -1 plus 0 plus -1, which makes -2. So you get V equals 1 over -2, or -half. And if you do it with X, the hard way, you'll still get -half. It's going to be the same. So we found V, which is the value of this game. The value of the game V is -1 over 2 as a simplified fraction. And then P star and Q star, you just multiply each one of these X entries and Z entries with -half. So multiplying this one by -half would give you 25 over 44, and multiplying this one by 5 over 22, and this one 9 over 44. So this is the optimal strategy for the row player P star, this matrix right here. And then the optimum strategy for Q, for the column player, is multiplying each one of these entries by -half, which would give you +half, 0, +half. So it's half, 0, half. That's the optimal strategy for the column player Q star. And that's question number 1. One last column. You may have noticed in the course material, when there is a 3x3 matrix, you can actually identify a recessive row or column and eliminate them and reduce this to 2x2, which makes it way easier to solve. But unfortunately, this matrix does not have any recessive columns or rows, so we can't really get rid of them. So that's why we have to solve this as a 3x3 matrix game, which is kind of long and hard, but that's how it's presented. So number 2 and 3 are fairly easy problems. In 2, the question is a yes or no, is this matrix scheme strictly determined? So for this to be strictly determined, it should have, if it has a saddle point, it's strictly determined. So let's figure it out. I copied it here. So to find the saddle point, what you need to do is, in each row, you circle the minimum value entry. So in row 1, you got -8, -1. Obviously, -8 is smaller than -1, so that's the minimum. In row 2, 5 and 7, 5 is the smallest, the minimum value in row 2. And then you look at the columns, and in each column, you put a square box for the maximum valued entry in each column. So in column 1, we got -8 and -5. So obviously, let me make this blue. So obviously, 5 is larger than 8. So we put a box around 5. And then in the second column, -1, 7. Obviously, 7 is the largest value. So once you go through each row and column, if you end up with a number, with an entry that has both a circle and a box around it, that's the saddle point. And here 5 has a circle and a box, which means it's the saddle point. So the value of this game is 5, and since it has a value, it is strictly determined. You say yes. You say yes. Yeah. And just remember, when circling and boxing, for rows, you take the minimum value. For columns, you take the maximum value. Alright, so number 3 is quite similar to 2. So again, it tells you this is a strictly determined game, which means it has to have a saddle point. Find the value of the game, and the value of the game would be the saddle point. So again, we're going to do the circling and boxing. So in row 1, you have 3 and 0. Take the minimum. So 0 is obviously the minimum. And then row 2, -2 and -3. -3 is smaller. So I'm going to circle -3. And then we do the same with the columns, but when it comes to columns, you take the maximum value, not the minimum. So in column 1, you got 3 and -2. 3 is larger. And then in column 2, 0, -3, 0. Sorry, we actually we need to take let me erase this actually. Yeah. So with columns, we need to not circle, we need to put a box. So 3 is the larger number in column 1, and in column 2, 0 is larger than -3, so we put a box around 0. So now, do we have an entry that has both a circle and a box on it? Yes, we do, which is 0. So that's the saddle point. The value of this game is 0. It's 0. So is this game fair or not fair? So if the saddle point equals to 0, this is a fair game. If it's equal to anything other than 0, it's not a fair game. So since the saddle point is 0, you mark B, it is fair. So number 4 is asking us to find the saddle values, optimal strategies, and the value of the game. So let's take a look at the matrix. The matrix is all of the 2x2 matrix, all entries are -2, which means the saddle value is going to be -2 because you can put a circle and box around all of them. So your saddle value is clearly -2. So in part A, you pick A and put the saddle value is -2, because when there is a saddle value, it is strictly determined, so you can't pick B. And then let's jump to C, and then we can come back to B. The value of the game. So the value of the game is equal to the saddle point, saddle value. So it is strictly determined, and the value of the game is -2. Very simple. And then in part B, the optimal strategies for R and C. Remember, the optimal strategies are for the row player. The row player is supposed to choose the row or column where the saddle point is located. And here, the saddle point is everywhere. So the row player can choose either row 1 or row 2, and the column player likewise choose column 1 and column 2. So you would put the matrix game is strictly determined from optimal solution. R can choose rows 1, 2, and C can choose columns 1, 2 or 2, 1. So that's the answer here. So number 5, determining which rows or columns in the matrix are recessive. So that means for rows, we're supposed to find any row that is like every single entry is smaller than or equal to the entries of another row. That's recessive. And for columns, any column that have entries that are bigger than all of the entries of another column. So there are only 2 rows, so let's see. So obviously -1 is smaller than 1. So we're going to see if row 2 is recessive. -1 is smaller than 1. -5 is smaller than -4. But -1 is not smaller than -4. So there's no recessive rows. So then we're going to work with columns. So let's look at column 1. And let's compare column 1 to column 2. So first of all, we have 1 and -1 here. 1 is larger than -4, and -1 is larger than -5. So column 1 is recessive because, remember, the column player always plays the column trying to minimize. So they would never play column 1 because every single entry here is larger than column 2's entries. So column 1 is recessive. So once column 1 is gone, let's look at these 2 columns, column 2 and 3. So -4s, they're equal. -5, -1. So obviously -1 is greater than -5. So here, column 3 is also recessive because these 2 entries are always larger than or equal to these 2 entries. So in this matrix, column 1 and column 3 are recessive, so you would pick B. So number 6, solving this matrix game and finding optimal strategies. So if you, this is a non-strictly determined game. Let's determine that. In row 1, the minimum value is -1, so circle that. Row 2, minimum is -4, circle that. In column box, the largest values, 1 is larger box. So in column 2, 4 is largest box. So there's no entry that is circled and boxed at the same time, no saddle point, non-strictly determined game. So these are the slides from the lecture notes. This is 10.2 section. Slide 10 gives you all the formulas you need. So the value of the game can be determined with this formula, AD minus BC over D, and these are the entries of the matrix, A, B, C, D, and D is here. So if you follow this formula, A times D would be -1 times -4, which is +4. And then B times C, another +4. And when you subtract them, you get a 0. So 0 divided by whatever is going to be 0. So the value of this game is 0 right there. So we found V. And then the optimal strategy for the P star, you do D minus C, which is -4 minus 1, which is -5. -5 divided by D, and D is A plus D minus B plus C. A plus D is -5, B plus C is 5. You subtract them, you get -10. So -5 over -10, half. You do the same, you also find that